All right, this is the pre-class video for section 5.2 exponential functions. The objectives we're going to go through are that we're going to define what an exponential function is and solve some exponential equations. Now we will briefly review some of the topics that are in the text below before our class, but I want to go through all of them in the pre-video as well. So the function f defined by f of x equals 2 to the x for every real number x is called the exponential function with base 2. So notice, to be an exponential function, your x, the variable of the problem, is in the exponent, not as like a term multiplied by the coefficient. So we are going to be plugging in values for x that are numbers, but those numbers are going to end up being our exponents on our base. So let us next consider any base a where a is a positive real number different than 1. Now the reason we don't use 1 is because 1 to any power is still 1, and that's not very interesting, and it doesn't have the same properties as the other bases, so it's not exponential if you use a equals 1. So it has to be a base that is positive other than 1. So to each real number x, there corresponds exactly one positive number a to the x such that the laws of the exponents are true. Thus, the following chart, we may define a function f whose domain is all real numbers and the range is the set of positive real numbers. So remember, that means that our y's are greater than 0. So I'm going to write that in. Sorry, my pen is having just a minute. There we go. So if our domain is negative infinity to infinity, I'll erase that in a second, and our range is 0 to infinity. That's a standard exponential function, the parent function as we've called them in the past, where we have f of x equals a to the x. Okay? So that's our domain and range. Now here is a picture of two different versions of our exponential functions depending on what type of base we have. So an exponential function f with base a, which we know as f of x equals a to the x for every x in the real numbers, where a is greater than 0 and a is not 1. So that's just definition of what it is. If the a is bigger than 1, so like 3/2, 2, 4, 5. What you'll notice is that as your x's get larger from left to right, your y values are growing exponentially. So this is what we call an exponential growth model. And then if your a is a fraction between 0 and 1, so like 1/4 or a half, a third, 2/3, then you'll notice that as you go from left to right, as your x's are getting larger, your y values are actually getting smaller. So you're not growing, you are what we call decaying from left to right, so you're decreasing. So the increasing and decreasing is dependent on whether or not our a, our base, is bigger than 1 or between 0 and 1. So that's the two different types. So the graphs in these charts show that if a is greater than 1, then f is increasing on the real numbers, and if a is between 0 and 1, f is decreasing on the real numbers. And this can be proved using calculus. We're not into that because we are an algebra course, but that is how you would prove it. The graphs merely indicate the general appearance. The exact shape will depend on the value of a. In other words, we can't say it's always going to look exactly like this. It could be stretched vertically, it could grow faster, it could grow slightly slower. So that is, again, something that's just, this is the general shape of an exponential function. Note, however, that since a to 0, so any base to the 0 power is 1, then the y-intercept is equal to 1 for every a. So as long as there's no shifting vertically or horizontally, your y-intercept is going to be at 0, 1 for a to the x. Now, this is just redefining what we were talking about above, the growth and decay. It says if a is greater than 1, this is case 1, then x decreases through negative values. The graph of f approaches the then as the x decreases through the negative values, the graph of f approaches the x-axis. Thus, the x-axis, this is important, is a horizontal asymptote. Now, what they're saying here is that if your a is bigger than 1, so 2, let's say we were doing 2 to the negative 2, that's going to be 1/4. And if we do 2 to the negative 3, that's going to be 1/8 because it's going to move it to the bottom and we cube it. So notice as our x's are going smaller and smaller, our y values are getting closer and closer to 0, but because this negative sign doesn't change the sign of the base, it just moves us to the denominator, you never actually go below the x-axis. So you're getting a horizontal asymptote. As you approach negative infinity, your y's are never going to go below that. So, and then again, you can kind of talk about it the other direction is if you're between 0 and 1, then as the x increases, the graph is approaching the x-axis. That means that as we go from left to right, we're going to the x-axis on the right side. So that's the decay function. And we talked about how if a is 0, then that doesn't make sense. So that's why our base has to be bigger than 1 or between 0 and 1. So 0 to the 0 power is undefined. And if a was 1, then we'd said that it's always 1 and it's a horizontal line. So these cases, case 3 are just kind of two special cases that don't really apply here. Okay, so what we want to do with this is the exponential function f given by f of x equals a to the x for 0 between a between 0 and 1 and or a greater than 1 is a one-to-one function. If you go back up and look at the picture, remember to be one-to-one, you had to pass both the vertical line test and the horizontal line test. So this does pass those. That means that we will be able to find an inverse function, and that'll be part of the one of the other videos and lessons that we're going to look at. And so what we know is that if we're one-to-one, that's what it's going to lead to. Exponentials are one-to-one, so that means logarithms, which we're going to define in section 5.4, are going to be our inverses of these exponential functions. So we'll teach you how to convert those back and forth. Okay, so the only examples that I wanted to do in this pre-video are solving some exponential equations using this property right here. It says if you can obtain the same base on each side of the equation, so like 2 to the x equals 2 to the y, then the only way that statement could be equal is if the exponents match. Because your singular bases also are matching, the exponents are forced to match to make the equation equivalent. So a lot of people like to say drop the bases. That's not technically what we're doing. We're saying that because of the equality of the bases matching and there's just one on each side, then you can't have anything other than matching exponents for the statement to still be true. So this is how we use this property. So we have 6 to the 7 minus x equals 6 to the 2x plus 1. So since we have one base on each side and they match, you can set 7 minus x equal to 2x plus 1. And we're going to solve this for x. So we're going to add that over, make it 3x, subtract 1. We have 6, divide by 3, and that says that x equals 2. Now we could check that. 7 minus 2, 2 times 2 plus 1. This is 6 to the 5th. This is also 6 to the 5th. So they do match. Now, because exponential functions have a domain of all real numbers, as long as you're not making arithmetic mistakes in your solving, you shouldn't have to check these solutions every single time. Now we need to talk about some special cases. This is 9 and 3. They do not technically match the way they're written currently, but 3 is a common base of 9. And we're not changing 3 to be bigger. You don't change numbers' actual values, so you can't make this guy 9. You can't just change it. But you can rewrite a number using a separate base. 3 squared is the same equivalent value as 9. So we are writing this way so we can take advantage of the laws of exponents. Now, laws of exponents say if we have two powers on the same base, we multiply them, so that's 2x squared. And now I have 1, 3 base on each side, so I can set the exponents equal. So 2x squared equals 3x plus 2. This is a quadratic, so we're going to move everything over to one side by subtracting those two terms. It's also a non-one in front trinomial, so we have to use our factor by grouping method. So 2 times negative 2 is negative 4. And the only pair that could make a negative 4 when we multiply, but a negative 3 when we add, would be a positive 1 and a minus 4x. So 1x and 4x. Pull out an x out of the first pair. That leaves me with 2x plus 1. Pull out a minus 2 out of the second pair. That also leaves me with 2x plus 1. We have our matching common binomial. We pull it to the front as a GCF. The leftovers are x minus 2. And we set both of these equal to 0. So there are two solutions to this problem. We subtract 1 and divide by 2. and x equals 2 I've already written, so x minus 2 equals 0. Kind of solved it while I was writing it. Okay, so that one is because it had a quadratic situation when we set it up, we had two solutions. And I could check both of these to make sure that the two sides equal the same value. It'll be hard to check if you plug it back into the original. You can't just see it as easily here because these bases already match, but you could check it on your calculator. All right, part C looks slightly suspicious because we see a 2 on both sides, but one of them's a half, so it's in the denominator. So when this happens, you can move the 2 back up and make it 2 over 1. What that does is it makes it a -1, as if we are undoing a negative exponent that's already occurred. So 2 to the -1 is the same thing as 1/2. This side would just be 2 to the first. We need to multiply our exponents because of our laws of exponents here. So 2 exponents on the same base, you multiply. So that changes both of those signs. Now we can set -6 plus x equal to 1. Add over the 6, and we get x equals 7. So this one was much quicker. If you plug 7 in, you get 6 minus 7 is -1. 1/2 to the -1 would flip upside down because of the negative exponent and become 2 over 1. All right, the last one that I'm going to do on this pre-video has two bases that don't match, and you can't make 27 9 to any power because 9 to the first is 9, 9 to the second is 81. But both of them can be rewritten as 3 to a power. So 3 to the third is 27, and you keep your exponent that's on the outside. 9 is 3 squared, and we are multiplying powers again. So 3 to the 3x minus 3, make sure you're distributing. And 3 to the 4x minus 6. Set your powers equal because your base is matching and you have 1 on each side, just like our property up above. Subtract 3x, that would just leave me with an x on the right side. Add 6 over, and I get x equals +3. And I can check that as well if I would like. But again, because exponentials have a domain of all real numbers, the check is not required unless you're just not confident in your arithmetic. That will change when we do logarithms because they will have domain restrictions. When domain restrictions exist, checks are required. Okay? I hope this video was helpful, and I will be working on the next one very soon.